Good morning and good afternoon, wherever you are. Thank you for joining this TDL webinar. Got a really interesting panel discussion to look forward to on demystifying digital twins. I could do with demystifying twins, but we're just going to do digital twins today. The session's being recorded and will be made available after the event, probably early next week, as will be a short report, which will be put on our Substack channel. We are very fortunate to have a great panel and a great moderator, Claire Vishik, who is one of our TDL strategic advisors. And with that, I hand over to Claire, who will take us through the next hour. Claire, over to you.
Okay, thank you. Thank you very much, David, and many thanks to our distinguished panelists for the discussion today. Today, we are going to discuss digital twins. This appears like a very or somewhat novel subject. In fact, I remember reading somewhere on the internet that it emerged in this millennium as a marketing approach. However, this is not quite true. The topic existed since the first space missions in the 1960s and all through the previous century. Those of us who started working in computing 20, 30 years ago, remember it in a somewhat different incarnation, the ability to present physical objects or physical processes in a digital form or link them with a digital form so that you could simulate them better, optimize them better, so that you could also link them better to the physical events in order to react to issues faster, in order to understand what is going on in the physical world in a way that is more efficient. But of course, with the advent of the internet, digital twins changed with the advance of digital and physical supply chains, starting with something like Amazon. The nature of the digital twins changed. And recently they took up a completely different form outside of the research community with large companies like Bosch, for example, representing in digital form their manufacturing facilities. Bosch, for instance, had a digital twin a few years ago of all the fabs that they have, 300 plus of them, as does Siemens. So today we have an opportunity to discuss it further, both in the academic and practical form. And we are fortunate to have a great group of panelists working on the subject or around the subject in various aspects connected to digital twins. And I am going to briefly introduce them. Their bios are available online. We are fortunate to have Ashish Khan, who is CEO of Intelligent Shop Floor. It's a startup in Silicon Valley. We have John Oakley, who is a professor of practice in computer and information science and engineering at the University of Florida. And we have J.V. Rajendran, who is associate professor and Ascent Fellow at Texas A&M University. We start with a view on the subject, an intervention that our distinguished panelists will share, and we'll go for this topic in the alphabetical order. Ashish, what do you think of the subject and its current state, its prospects, and interesting aspects of the area where you have the greatest interest?
Yeah, so digital twin, I have actually used digital twins for my customers. So for last, I'd say since 2009, I have been involved in um, smart manufacturing space. So essentially, the Industry 4.0 initiatives have helped many plants worldwide, steel plants and large food and beverage companies, and so on and so forth. And digital twin had played a very key role in almost over the last 15, 20 years in achieving the so-called the Industry 4.0 initiatives, like using the digital twin and monitoring the critical assets. I see, it has evolved in three stages. In the beginning, the first stage was the 3D model, like a process map or a simulation. Those were useful, but mostly static, like a 3D CAD model of a CNC machine is a good example of this kind of a thing, but it was not connected to live machine data like the spindle load, vibration, temperature, etc., etc. The second one is what you are talking about, and you gave some good examples, which is sensor data flowing from the physical asset into the model, so we can monitor condition and performance. And some of the real world examples are like the Rolls-Royce aircraft engine, which is the digital twin. It's widely publicly available, the information. The physical engine continuously streams sensor and operating data and connected back to its digital model. And that model is not just a static simulation, it is updated by the real engine's condition. As a matter of fact, they started this concept very early, which is the Power by the Hour program. And that is in manufacturing, but there are a lot of examples. For example, actually in England, since David is in England, they had these Thames underground, the water network. They used digital twin extensively for leak information and so on and so forth. Singapore is a good example. They have a virtual twin, which is a high resolution model that integrates buildings, infrastructure, population movement, environmental data, etc. And what I am doing work in intelligent shop floor is the entering into third stage, where it is synchronized with the physical world and helps us predict and prescribe and sometimes act back on the physical system. So we use the world model, where it is actually based on principle of physics is involved. So the welding machine actually know its environment. So when we are monitoring, we can actually know that at what speed it is going, whether the humidity in the factory, so on and so forth. So I think in one sentence, if I have to describe, the future digital twin is a sort of a decision engine infrastructure connected to the physical world.
Thank you very much. That's a very good summary of the field to start this discussion. It's sort of clear in what areas the digital twins are the best positioned to provide the best outputs, to provide greater efficiency. What are the areas, in your opinion, where it's more difficult to use them, and why?
Who are you asking me about?
Ashish,
Somebody else?
it's for you. Yeah, it's for you. Yeah.
So you're saying where it is difficult? I think some of the challenges, you mean?
Yeah, some of the challenges that some areas of the use of digital twins experience. For instance, not enough data of a certain type, too much data, not enough anomalies to provide a good feedback on what's going on, and so on.
Yeah, first of all, what I have felt in the field is the brownfield factories are hard because the equipment is old, data is fragmented, the OT, the operational technology, IT, information technology systems were never designed to work together. Then I'd say cybersecurity is another problem. Cybersecurity risk increases because the twin actually connects the digital systems to physical operations. There could be also regulatory and validation issues matter in aviation, healthcare, pharma, some critical infrastructure. And this is why, what I have observed is that many companies started a pilot, but they struggle to scale it across plants, assets, workflows, and so on. So those are, some of the barriers. And as you correctly pointed out, this data integration is always hard. Doing a data warehouse kind of a thing is hard. Another challenge, by the way, I recall is they all want to connect different, like a twin to twin technologies. So system of systems, that also has a lot of challenges. I have not seen many successful twin to twin kind of a where you connect the multiple twins together and make a decision making. So those are some of the challenges I have faced. Thank you.
Excellent points. Excellent points, Ashish. Thank you. As in many large data-driven systems, integration of different components is one of the main issues and the greatest concerns. We are going to, one of the greatest concerns, we are going to address it later. Let's now move on to other views on the subject. John, what do you think?
Yeah, digital twins are as you said, a concept that we've been working on for what, 6 decades now, from the start at NASA. But I think we've really only been talking about that, let's say, terminology for the last 15 years or so. Um, I think we have built many systems where we then model it and try to provide feedback. I think the core of the digital twin idea is that we do have virtual systems and physical systems that are interconnected, that what we see in the physical system informs what happens in the virtual system and vice versa. I do think that digital twins allow us to abstract in ways that we couldn't do before. It allows us to share knowledge in ways that we couldn't do before. I do think a lot of times we have digital twins that are a model that is informed by a system that we can play around with, and we expect the physical system to follow along the same way, and then we have feedback that says yes, it does or it doesn't, and then we learn from that. I think one of the big challenges, as you said, was connecting digital twins, because as even though terminology has been around for a while, there's no clear definition of what a digital twin is. And I think a digital twin looks different depending on where you look at it. A digital twin for an engine looks very different than one for a semiconductor etching process, but both are valid digital twins. I do think as we look at some of these, we'll call it chemical or manufacturing processes and things like that, I think we probably can make digital twins that are advanced enough that we could actually do exploration with these, uh, and say, okay, what I know that with this set of materials, I've had these results, and what if I had a material that looked like this? And then try to find a material that looks like that, and then test that and see how good was my model, or how do we need to retrain and do things like that. So I do think there's a lot of opportunities. I do think uh, probably the biggest question that we have right now for digital twins is uh, that term is so used in so many different ways. How do we, let's say, make it specific enough for what you want it to do versus useful enough to actually do what you want it to do? right? So there's so many definitions, so many iterations of it, and I do think that that's one of the biggest challenges is, okay, a digital twin looks so different depending on how you look at it. But in the long run, it's a virtual model uh, that is connected to the physical system, and you can have real-time or near real-time feedback between these systems and learn from each other. Uh, yeah, I think it's a great opportunity, but I do think there's work to be done to make these the interconnected world of virtual twins that we will have in the future.
Um, Thank you very much, John, for an excellent introduction to the topic. And you are really correct when you are saying that the digital twins, because it's in part a marketing term. At the same time, it is a technical term in some areas. Does not have a strict definition, and I have seen it even in technical conferences used in completely different
Yep.
fashions to describe phenomena that are not connected to each other. If you were to give a definition of digital twins for your area, how would you define it?
Well, I think a digital twin is um, it's a virtual model that's informed by the real world, that learns from the real world, provides bi-directional feedback between those things. Uh, because the digital twin could say, okay, here's how we could improve it and things like that. Uh, it's hard. I know that's kind of a circular argument, but the idea is that it's a virtual and a physical system that are interconnected and feed each other and learn from each other. Uh, and so I think a digital twin has to have both. If it's just the model, then we're not really learning from that. If it's just feedback in one direction, then that's not really achieving the goals of the digital twin. The digital twin needs to have, let's say, that bi-directional feedback between those systems. And adjusting a physical system is not quick sometimes, most times, right?
Yeah, thank you. It is a good definition. It's a virtual model, it's bidirectional, it's connected to a physical object. I think this is more than most traditional definitions give us. Thank you very much. JB, like you probably, my first encounter in practice with digital twins was in conjunction with research topics associated with electrical engineering and semiconductors to some extent. And then I used it in different contexts. In different contexts associated still with similar environments. What do digital twins mean for you? What do you think it is? And what do you think its current state?
Yeah. So first, let me start with the caveat that I am not a digital twin expert. Uh, 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 the things I've been going about this topic is basically talking to my colleagues, reading papers, and trying to educate myself on what digital twins and things like. As John and Ashish pointed out, there is no one uniform definition. When you talk to different people, you get a different definition. And um, yes, you mentioned that NASA has been doing this for 60 years for many of its avionics. And it seems like the digital twin topic, when I talk to my aeronautical engineering colleagues, they have been doing this fantastically. And for many, many decades, you can see many big companies like Boeing, they have been doing digital twin of avionics equipment for a long time. But then sometimes I ask the question, hey, isn't the semiconductor engineers do the same thing? We have been building spice digital models, which we interact, that is a reflection of the reality, or that is supposed to be the reflection of the reality, that we can interact with real time instead of waiting for 3 to 6 months from the foundry to give what my circuit is, and then going and poking what the circuit output going to be for different inputs. So, and that is informing my engineering, right? Like if I pick these circuit parameters, this is what the output response is going to be looking like. And therefore, I'm going to tweak this here and there to get what I want. And that seems to be a digital model informed engineering, which seems to fall under the digital twin umbrella. But I believe this goes beyond that, right? So from an electrical engineering perspective, or your question is, okay, what does it mean for me? So my area is mostly in the hardware security space, even a subfield of electrical engineering, and computer engineering, you may call that. So for me, I would like a digital twin that can go and do the attacks for me, right? Like, hey, if I am designing a system like this, and I put my chip based on this design, I created my chip. Now, how susceptible will that chip be to a side channel attack, to a fault attack? What other ways attacker can tamper with the chip? How would the chip respond to different excitations from the attacker? I would love to see that, right? Because then I don't need to build a chip. I don't need to pay Global Foundries $18,000, even though they reduce the price for academic. It's still a lot in this funding situation. So a model like that will greatly benefit academia and even more greatly benefit industry, so that the designers can inform about security whenever, as and when they design the chip. Now, taking a step back, it's not just security, right? There are many new multi-physics effects coming into place, and the designer need to be aware of all these effects. Previously, I thought, hey, it's the problem of the device engineer. They need to handle all the multi-physics problems when it comes to chiplet design, different styles of packaging. And no. That is not the case now, right? Now people say, hey, even the architecture guys need to be aware of this multi-physics effort. But how many architecture people are experts in multi-physics? And like multi-physics simulations, they take a long, right? People spend decades and decades of career to master the art. So having this style of digital twin can act as an interface between, for the lack of a better word, a non-expert to bridge the knowledge gap so that they can get what they want to do their work effectively.
What an excellent way to describe it in this context. Thank you very much, JV. What do you think the assistance that digital twins provide in this context should add that it doesn't have now? In other words, what are the promising research directions? A little bit of personal context. Back in the day, when one of my projects was physically unclonable functions, that area was completely simulated in FPGA, sometimes in software. We got funding from the European Commission at some point and implemented this in silicon, different types of physically unclonable functions. The implementation in silicon had different properties than what we anticipated in simulations. This is obviously because, even 12 years ago when that was happening, it was a different world. There wasn't a good way to handle the data. And when simulations were built, a limited number of sources of interest were considered. How can it be different now, a project like that, or a project like you mentioned with regard to designing a chip?
So the physical unclonable functions are a very good example, right? So there, in physical unclonable functions, so for people who may not know what that is, shortly called as PUFs, you are trying to extract the device manufacturing variations, extract the key from the device manufacturing variations. And the fundamental concept or the reliance of pulse is that you cannot model or accurately model such effects. And that is why it works. At the moment you can accurately model those effects, they no longer provide security guarantees that they are supposed to provide. Now, on the digital twin end, the definition is conflicting because here you want to accurately model certain physical effects, right? So that you can make physics-informed decisions real time. So you can see the contradictions because pulse requires something you don't want to you cannot model, whereas digital twins, they require you to model, right? But you don't need to model the accurate. Many times what we are seeing is that researchers seem to trade off between accuracy and simulation complexity, and even trading off accuracy for speeding up the simulation. They are still able to make many good results, right? Like even like the spice models that we use, there are like different levels of granularity, and depending upon the question that you are asking, sometimes you can get away with a relatively less complex model, simulating a less complex model than going for the detailed physics model.
Thank you. It's certainly true that the ability to implement complexity and flexibility in how the models are built are an excellent driver to propel this field both in research and in practical engineering context. Now, let's talk about the main drivers for the field. I read market projections recently from various market research companies, and this market, without actually a strict definition of what it is expected to grow very, very fast in the next 3 years. If this happens, what do you think will be the drivers of that growth? Ashish, what do you think?
Yeah, what I see some of the drivers is the availability of sensors, because a digital twin, typically, let's say a pump, right? We put vibration sensors, we put temperature sensor, and also we get both the electrical and the mechanical signals out of it, right? The torque, the speed, et cetera, as well as the current, voltage, and so on and so forth. And as you know, thanks to the smartphones and all that, sensors have become very cheap. And new innovations are happening. You mentioned Bosch. They obviously make a lot of these sensors. And there are sensors, I used to work with a company called Everactive, which they created the batteryless, because, something is vibrating. So batteryless vibration sensors. So they were generating they were using the vibration itself to get the power. Then, another thing is that there are a lot of soft sensors using the cameras, right? So what is happening is, many of these sensors are becoming cheaper. Then the connectivity, the storage, everything that you can think of that are required for the digital twin is becoming cheaper and cheaper. And then finally, the AI itself. You can actually, and another thing, coming to AI in a second, but all of these companies, all the cloud companies like Azure and AWS and so on, they provide a easy way to create these digital twins of any asset. And since all the data people are bringing to the cloud, so it becomes very easy. So the ease of deployment, ease of implementation are becoming also helping the growth. And to some extent, the area I am working on, the causal AI, or to some extent, you can call it neurosymbolic AI, meaning the neural plus the symbolic logic combining. So in the causal AI is also becoming, so now it's the digital twins can be used not just for what happened, but also, why it happened, and what to do about it. And, some of the autonomous things maybe we can do now, and the what if analysis, right? That if I had done this, what would I have done? This is quite, digital twins in supply chains are widely used these days. What happens? There is a union strike in some plant. What happens? There is a weather change. What happens? The Hormuz, this thing is closed. So you can simulate these things. So I think, people are using a lot more of these digital twins, especially the things that are very hard to do it physically. Like, some of the best examples are obviously aircraft engines. GE showed the wind farms where it'll be almost impossible to go and do in where actually the wind farms are. So and many of these are being remotely operated. Many of the oil and gas companies operate in remote places and so on. So that's why I think that because of the technology driver, the economic driver, and the remoteness of many of the assets, and it is becoming easier and easier to build this model and apply AI. That is also driving. And lastly, I will make a point. I was in a German company called Munich Re. I was part of their IoT group, and we worked with a company called Trumpf. So they were using digital twins also for another reason, which is the as a service asset. So they used to make this kind of laser-based laser cutting machines, and they were offering this as a service, so you don't need to use your capex. So in Germany and Austria, etc. So people take sheet metal and they create these specialized metal objects mainly for car industry, but for other also. And they were able to, because they are constantly monitoring how it is being used, how the machines are used, and their motivation is to highest availability, because that's how you are charging. I mentioned about the power by the hour of Rolls-Royce. So these type of models are emerging. You have a new revenue sources, recurring revenue, and you can also sell these digital twins. So you're actually monetizing this. So that is also driving the adoption of these digital twins. Thank you.
Thank you. JV, what would you like to add?
Yeah, so I would say digital twin being a very good proponent for many startups. So let's say as a startup, you are focusing on developing a very niche technology, right? But usually one of the values of that is that you want to take the technology and see how it serves in a broader sense. Let's say, for example, I have a new idea for EV charging, right? If I go and say to Tesla, hey, let's replace all your EV chargers with my new idea, they are gonna balk, right? Like, hey, go away, right? That is a reaction that is gonna get, right? So if they can make the digital twin model available and say, hey, if you want to work within our ecosystem, can you enable your technology work with this digital twin? And if it produces promising results, then let's consider deploying it in a real, or even in a small scale real world environment, right? Previously, this type of mechanism was largely unavailable to startups, right? Because as a startup, I want my technology to be widely used, and many times it's usually the big companies that are going to deploy the technologies. And I believe digital twin can be the bridge helping the startups to navigate this ecosystem imbalance.
That's an excellent point. A follow-up question. For you, JV, one of my first encounters was one incarnation of this technology was in oil and gas, where drills are very expensive, and that's why predicting, the strata, how hard they are going to be in order not to break the drill, is very important. Sensors to do this had been available for a very long time, maybe from even 1920s to some extent. But the ability to process the data that comes during the drilling process in real time, which is necessary, is relatively new. And even in the late 1990s, early 2000s, there was this massive data that could be roughly processed in near real time, but not with the detail that it was needed to avoid breakages and optimize the process. Do you think it is different now? Well, we have better sensors, we have AI, we have more computational capabilities, but we also have a lot more data. What do you think is the situation today?
So definitely you are not you are collecting more and more data because a lot of advances in sensors, right? But also you can because of the advances in actuators in certain applications, not all, you can actually stimulate the environment for hey, what happens if I tweak it this bit, what happens this way, and so on. And you mentioned oil and gas, right? So previously, I believe many of these advances are isolated even within a particular field. So meaning if I want to focus on the drill, I will just focus on the drill. I will not focus on the pipeline, right? I will not focus on the refinery because if they are all operating in individual silos. But one of the advances of digital twin that people are looking for, right, is that they want to see the entire supply chain. Given many disturbances in the supply chain, they want to see, if so and so gets affected or so and so drill is not working at this hour, how will it affect my refinery? How should I do my scheduling and things like that? Right. So they are looking for the entire supply chain. Now, and this is not just oil and gas. This is almost every industry, particularly the semiconductor industry, where there is always like, hey, one metal is not available. There is critical shortage of this metal, or there is some political conflict going on. So all those things, right? And you need many of these things to make the chip to be manufactured. So the digital twins, they do pay a good way for these type of supply chain problems.
Thank you. I agree. John, what would you like to add?
Yeah, so listening to both Aziz and JV, I think these models they're becoming like the experts. We're experts are working with these models, training them, but the goal, I think, ultimately for these digital twins is to democratize knowledge, because the average person doesn't know the specifics of this or that or this, but when you connect all these things together, they democratize, they make it available, let's say for the startups or for the companies, or just making these connections. Uh, I mean, it's the same idea with the agentic AI. We have agents that are doing specific jobs. We then connect it with a larger system. Digital twins are the same conceptually as that. They're just connected more to the physical world. Uh, I do think that democratization of knowledge is the wave of the future and will be the way that people work with things, because you'll be expert in your area, but you won't necessarily know the 100 other things, other materials, other processes, shipment times, and is the Strait of Hormuz closed or whatever that's going to happen. And how does that affect the job I want to do about actually just making the thing that I want to make or work with the thing I want to work with. So I think ultimately these digital twins will help us make things more available, knowledge more available, operations more available, and will then accelerate research and development and operations across the board. We have a ways to go to get to that level, but I do think that's what's ultimately going to happen. And with the new AI models and new things like that, those are all in kind of in line with that idea that we have, let's say, focused experts that do something, a model, a AI, agentic, a digital twin. We connect them together to a bigger system. That bigger system then does more than the sum of its parts. And I think that's where we really see the potential for digital twins. Uh, and I think, yeah, aviation's been doing this. They model them like a engine, and then they put it on a actual plane, and then they model the airflow of the plane, and then when they put those together, they can learn more than just one piece or the other. So I think that will apply to pretty much all fields of study, uh, and all fields of interactions, uh, eventually.
Thank you. That's an excellent point. To drill down on this, the democratization of knowledge certainly is important. It makes even specialized knowledge available without considerable expense to a much wider group of people. But there are downsides to this. One of them is that sometimes we have to sacrifice accuracy. The other one is sort of the erosion of expertise in the field because answers appear to be available, but there isn't always the ability to critically assess them. What do you think, John, are the challenges in introducing digital twins, especially in high precision fields like aviation?
Yeah, so I do think that they will allow us to make advances and see connections. I mean, that's why digital twins are actually a kind of an improvement over just looking at a pure agent-based AI, right? Because the agent-based AI is not, since it's not necessarily informed, it's informed by its training, not by something that's happening in the real world. And because it's not informed by, let's say, real world feedback, it's not learning about what's really happening, and it could manufacture, create false data, false operations, and then I mean, I think we've seen this plenty of times with our current AI models, right? They create false information for people all the time, and then people believe it. I do think as uh, we have these systems, people will assume that what it's saying is correct, because they don't really have the knowledge to disprove it. So without a reason to not believe it, most people will believe it. And so I do think that is a challenge for what we will have in the future. I do think it's a great opportunity for us to have these specialized agents, digital twins, whatever you want to call them, that can have that knowledge. I do think having them also makes some knowledge that people might want to keep, let's say, more secure, more private. It'll be more available with these. So there is, um, it's a double-sided coin, right? So it'll be more available. People assume it's real, but then people also uh, not have won't actually question it, and then that's actually not necessarily a good thing. Let me yell at my
Not
dogs.
necessarily a good thing. This is very correct. Thank you very much, John.
Sorry.
Ashish, what do you think are the challenges to the deployment of digital twins, and what technology innovations do you think are going to help us compensate for those challenges?
Yeah, actually, John hit up on a very important point, which is digital twins. You create a digital twin, and the purpose is not to use, not to just create a digital twin, but to use it for, in the manufacturing or some of the examples we gave in the aviation as to replace these routine maintenance by just-in-time maintenance, and also. And therefore you use AI. And as John kind of alluded to it, the current AI is based on the pattern recognition, right? Meaning correlation. So the correlation, as so many people have said, correlation is not causation. So if you can add the physics informed or first principle in based models, that will definitely work. And that's an area I'm very interested in. And the other challenges are, I think either John or JV also mentioned is the connecting this, because we want to create a system of systems. And they have been trying this, especially, like many cities are trying to simulate, okay, these are the digital twins of my buildings, these are retails, these are, the whole city, their model, and they want to see what happens when there is a crisis of some kind, the hurricane is coming, or I'm from California, so we have these wildfires, right? So all these simulation, but it's not easy because and the other thing is that I have tried this before. Let's say I buy a compressor or a company X, they may not be able to give me a digital twin, so I have to build it. Building digital twin is not easy, right? And let's say I use that compressor to build something, then I already have 3-4 different elements, critical elements that I want. So connecting those twins is a problem. There are, Microsoft tried with a language like DTTL, digital twin language specifically, but we don't have a standard yet. So that's one of the challenge. And then, I already mentioned that if it is remote, then obviously you have to think of, data coming in and all that. Is also, it has its, the connectivity issues are there. And as you said, there is lots and lots of data these days, right? Handling all this data, those are also challenges. You hit up on, Claire, you hit up on one interesting thing is that we have tremendous edge computing capability nowadays. So, you were Intel, I was at one time Intel has these neuromorphic chips coming out, and so many others are also doing, which will help with some of these calculation, the inferencing part, not the training part, as an example. So it's not a GPU issue necessarily. So those are already happening. And causal AI, a lot of startups are now, like myself, we are also trying to enter into those areas and help these digital twins, more active digital twin rather than passive. So those are some of the things happening. And last thing I'll say, another thing is happening, as John mentioned, democratization. We have the universal way to interact with systems. It's called AI. So anybody who has used ChatGPT and plugging in, that's the natural language we are using. So it is becoming frontline workers can easily handle this model and ask question, do the what if analysis. So that is also will be more and more, the LLMs will be integrated with these things, specialized LLMs. So those are all the current trends that I see as going to take digital twin to its next stages.
Yeah, thank you. Active digital twins, very interesting. Certainly something that I can see immediately the opportunity to apply in many areas. JV, what are your thoughts?
So, as Ashish is describing, like how many different entities are looking at the digital twin, one thing that comes to my mind is how do they all interface, right? Everyone is developing their own digital twin, because based on their expertise, based on the data that they collect. But at the end of the day, we want all these individual entities to work cohesively as part of a larger system. So to enable that, maybe some type of standardization or standard interface model will help the community a lot. And this is the same problem that we faced in the chip design, right? Each and everyone will design their own module with their own interface. We don't know how to integrate them. But then people said, hey, look, here is companies came together and defined standards. Hey, here is how you are going to design an individual block so that everyone interfaces in the same way, and internally you can do whatever you want. So some type of standardization so that all these individual pieces of expert digital twins can all nicely fit together to make the big picture.
Thank you. Talking about chips that are becoming more and more complex these days, and having been part of many projects trying to find the root cause of some issue, which is incredibly complicated. Where do you think, and if there are limitations of using artificial intelligence to find patterns that are not yet known, to recognize patterns that are not yet understood, what do you think? JV, that's for you.
Okay. So the democratization part is okay. It enables different, it kind of like levels the field. It lowers the barrier for entry, especially for smaller players. But let's also be honest. Companies who spend millions, even billions of dollars developing a digital twin model are not going to give it away for free. Yes, like consider the example of like ChatGPT, right? The OpenAI, they have a free version that you can interface, have certain token limit, but then you have the subscription version where you pay and you get like a lot more features. I feel like this is the way digital twin may also go. I mean, even companies in chip design, they have something called trial IP, which is, hey, if I want to buy a processor, they give me the trial IP to make sure that IP meets my needs. But it works only for certain number of hours or certain number of weeks, some time limit there, or some other rate limiting factor there. And then once I'm happy with this performance, I will buy that IP by paying the company, and I get a full-fledged version along with the support. So something like a tiered models, tiered version of digital twins to enable easier evaluation, assessment, and see if it actually works in whether a particular digital twin works in my ecosystem or not. I think that type of tiered model can help the democratization process a lot easier.
Thank you. An interesting point of view. I rarely thought about democratization, but of course, with such diversity of designs, so many IP inserts, even in simpler designs, it's important to introduce something like that to a greater degree that it's available now. Thank you for introducing this thought. John, what do you think are the longer term prospects? Of course, now this is one of the buzzwords for market research. Everyone is very optimistic in this technology taking over a lot of fields. What do you think is the case? What are the limitations? What are the prospects?
Yeah, I mean, I think we'll talk about the limitations maybe first. I do think the digital twins are as good as the systems they're based off because they are a bidirectional feedback. Sometimes they are very specific, and we actually maybe not even collect enough information or the right information to really model a digital twin. The digital twin will work on the way that we assume that it works because we don't necessarily collect all the data on all systems. So if we do have a process or a device or whatever, we have sensors that collect data. But are those the right sensors? Are those the right things? Are we missing something about it? It could be that the most important piece was actually not even captured. So therefore, you will see an issue where some digital twins, some models will not take it. Like you said, the case, the puff. The puff is designed because we don't know all of the different parameters that we need to measure. If we could measure them all, it makes some things obsolete. But I think that that's a challenge that we will see in the future. I do think we will learn more as we develop and deploy and connect and utilize these systems. And I think that knowledge and usage and iteration will actually achieve more in the long run. Probably the biggest thing right now is what level does a digital twin need to be? How many levels do we need to support for a given process, a given situation, a given whatever? Uh, how do we connect these things in a holistic way? Do we need to have uh, interfaces, or is AI going to be smart enough to connect these things for us without having to have a standardized interface? Maybe. Uh, right? If you tell it what it does and it figures out, okay, here's what an interface is with what you have, uh, maybe that's something we can do. I mean, I think they're making assumptions about those things. The more rigid we make some of these things, we may actually hide things that were actually important. Uh, so I do think that's a big challenge. I do think that the future is bright for digital twins, and I think they will become a mainstay of pretty much all of the processes, from manufacturing to process development to transportation and smart manufacturing and smart transport and smart factories and smart homes. And uh, we'll have this aspect across the board. And a lot of it, most people will not understand. That's kind of the thing. It's like, and they don't want to know. Realistically, they want to know that the information that okay, here's what's might happen if I turn off like we know if we turn off the power to our freezer, it's going to go bad eventually. Do we need to know if it's 4 hours or 8 hours? Most people don't need to know that, but some people do. And if you do, that digital twin could probably give you some of the information. And the average person says, okay, it's probably bad now, but I mean, it's just an example. We have plenty of data that can correlate this, but if we actually had more data or the right data, we probably could do better jobs and have a better future for these things. I know I don't know. I don't know if I answered your question, but I do see that there's a lot of opportunities, but there are challenges to make these things and figuring out what the important pieces, what the important parts to connect within the digital and physical worlds. Uh, it's probably the hardest part of most digital twins is figuring out what the actual most important parts are.
Thank you. And it's good to see that despite the challenges, you are overall optimistic about the potential for growth
Yeah.
in this
Yeah.
area. Thank you. Ashish, what do you think? What are the long-term prospects? Is it going to grow as expected, or is it going to fizzle?
No, I think it's going to grow. I mentioned some of the factors. One is this is another way of monetization of data. We are collecting a lot of data, but how do we monetize, right? So you could, just to give an example, that you could provide a digital twin for an critical asset for insurance company or a lease, the banks as an example, and they can see who are some of the safe users or who are operating this equipment properly, right, within the operating conditions that are prescribed by the manufacturers. Then there are obviously, in a factory setting, the cost of unplanned downtime is going up and up and up. In automotive industry, I read a Siemens report. It says on a hourly basis, it comes to a few millions dollar. In some plants, ABB said it's $125,000 per hour. So you are preventing this, and so we have done enormous efficiency, but part of efficiency is that if things don't go as planned, then you lose more money because there are fewer people, there are more gadgets, and so on and so forth. Fab is a very good example, right? My God, I mean, you have to scrap some wafers. Wow. So these are the reasons I think that people will use digital twins to do these predictive things and so on and so forth, get the data, and it will build on itself. Like John was saying, you give these models to each other and build the whole ecosystem. system of systems, right? So I am very hopeful about the proliferation of digital twin.
Thank you. And it's great to have another optimistic view that despite the current challenges, and we mentioned quite a few of them, there are opportunities that will propel probably digital twins towards common use in some form in different areas of operations. JV, you get to say the final word of this panel. What do you think are the long-term prospects of the technology as you see it? Are you optimistic?
Yes. So this is very exciting because it is. I mean, I want to use the word new model for how the industry operates, but no, that's been there for 50, 60 years, right? But the concepts of physical AI, it is adding many new dimensions to this, and incorporating them into the digital design and the engineering flows will be very exciting to see how that operates. Number two, companies are far more freer and happy to exchange their data compared to the historical trends, and which means that more and more people are going to get access to the data and develop new technology and solutions. So that will be exciting, and how and lowering the barrier of entry by having some type of standardization, tiered models, cost models for digital twins. That will also be super interesting. The final thing, since I work in security, I am very biased, right? So that towards the topic. So like the cybersecurity of digital twins, because I know you are going to make engineering decisions based on the model that I am developing. What crazy things that I can do in my model to screw up your engineering decisions, and what kind of solutions that you need to have to safeguard your engineering decisions based on untrusted models. These are exciting questions, not only for industry to answer, but also for academics and students listening to this to start working on.
Thank you. Indeed, it's an exciting time for multiple technologies, including this one in various areas that include security. That's also dear to my heart. Ashish, John, JV, thank you very much for joining us today. Thank you so much for giving us so much food for thought on this subject and in adjacent areas. I will certainly think about this subject a lot more in the near future based on the ideas you shared today. With this, I pass it on to David to close this panel.
Thank you, Claire, and thank you, Assis, JV, and John, for a really interesting discussion. I've learned an awful lot. Well, that wouldn't be difficult. I've learned a lot, everything I know about digital twins in the last hour, and I look forward to hearing more about it. It seems to me, I agree with all the panelists and with Claire, that this is a technology and a solution, along with many others, that will continue to grow in the future. And hopefully we can come back and revisit this sometime in the future and hear more about it. And with that, thank you very much to all of you.